to linear algebra done right by Sheldon Axler. So it's actually been a long time since I started recording because these classes have been really overwhelming me, so I decided to drop class today. It is pretty tough recently, and I've been trying to look at this problem for a very long time, as you know, and I have to issue a correction for the previous question. So for the previous time I did question 17 in section 3D because that was entirely wrong. So I'm here to redo that question. I've talked to the professor and he gave a proof which was very difficult to imagine if you're not familiar with matrices, which I sort of like to think abstractly when it comes to this kind of thing, but he is very familiar with such properties in matrices and working with matrices, etc., that this is natural to him. So I'll present what he said here. So first, it's not difficult to show that if epsilon is the zero set, or if it's the set of all operators, then it's closed by multiplication from the set of operators. The issue arrives when epsilon is somewhere in between, when epsilon contains a value or contains a map, let's say some t, which is not 0. Then this is the issue which we wish to discuss. So then I think what he said, which I found interesting, is first, if you have some sort of matrix, like just some generic matrix, and then you have a value which you want to... So this is a very tricky thing to think about. If he hadn't told me, I would never have known this. Say you just have a generic n by n matrix, and the way you would think like this is, say n is the dimension of V. So if you have an n by n matrix, then what you must do here is kind of contrived. Once again, I don't like it, but it's how it works. Sometimes in math proofs you have to sacrifice the intuition for results, and it kind of sucks, but that's the way it is. So I think once you imagine a matrix where only the top left corner has 1 and the rest of it is all zeros, then you multiply whatever matrix you have against that matrix. And then essentially you select only the first row and the first column. You only select this exact entry, and the rest of the matrix is zeros as well. If you're not convinced by this, then certainly feel free to try out an example, and I will try to do something like that here. So if you multiply this first row against this first column, only this 3 will be preserved, the rest will be multiplied by zeros. That's your 3. And then if you multiply any other row with this, oh wait, actually, no, this will preserve the first, oh no, actually this will preserve the first column. What am I doing? Of course. Okay, that's not good enough. You need to get rid of the first column somehow. Oh shoot, what did he say? Yeah, I screwed up. Yep. Because I think what he said is that there's a way to turn any matrix into something which only has one selected non-zero entry and the rest is all zeros, and then you can do that somehow. Okay, let me check what he said in the email, because once again, this is not something you are able to just think about casually. He's a very experienced, obviously he's very experienced at linear algebra, but Um, this is a very strange thing to think about. Okay, yeah, so oh never mind. Okay, yeah, I'm just reading what he's saying. Okay, yeah. So I think the first thing when you have a generic matrix, the first thing which you ought to do, so let's say you have some non-zero matrix in epsilon, then you take it, and then you perform Gauss-Jordan elimination or reduced row echelon form. Then what you end up with, I think, is that it has to be an upper triangular matrix, right? So if you end up with the identity matrix, then you're lucky because you're already done. So, of course, Gauss-Jordan or reduced row echelon form is also a series of matrix multiplications. So you can think about the series of row operations being associated with one matrix multiplication each. And then when you perform multiple row operations, you're actually multiplying by multiple matrices. And all of these matrices are still in this, what's it called? They're still in the operator space. So then, if you combine all of the row operations together, and say you have n row operations, then combine them together to form a matrix R. When you multiply all of them together, and then apply this matrix to T. So either you get I, or you get some sort of upper triangular matrix. If you get the matrix I, then you are basically done, because note that our assumption was that whatever matrix in the linear operator space you multiply T by, you still get something back in epsilon, because T was in epsilon. So whatever matrix you multiply T by, it still ends up in epsilon. So let this R be in this LV, for example. And then when you end up with the identity matrix, what you have here is you can multiply by any element of the operator space by this I, and it will still end up in epsilon, which means that LV is a subset of epsilon, and epsilon is a subset of LV. So these two are equal, in fact, and you're done. But if you have a non-zero matrix T, which is in epsilon, but you don't end up with this identity matrix, which means it's not invertible. So T is like some sort of not injected, not subjective, not invertible operator, whatever you call it. Then you need to perform something a bit more complicated. So now note that since you have this upper triangular matrix, so observe that the upper triangular matrix will have a lot of zeros in the left bottom corner, while having some arbitrary numbers we don't know about in the right top corner. And across the main diagonals, you might see a bunch of ones, but you trail off at some zeros. But if you multiply this matrix by the matrix with only one in the left top corner and everything else is zeros, then in this way you are forced to get just one in the left top corner and everything else is zeros. And the reason is because previously when you multiply these two matrices, you preserve the first column because of this top left corner one. But since the rest of the column the rest of the first column except the first element has to be zeros, because you perform reduced row echelon form, then indeed that when you multiply by this matrix, you end up with only one in the left top corner. And then this is the matrix with which you are left. And then with this matrix, this is where the weird part begins. You can you can actually shift this 1 to anywhere on the main diagonal. And this is quite believable because eigenspaces, eigenvalues are preserved through similar matrices. I know they don't talk about eigenvalues until much later, but if you know eigenvalues, then it makes sense that the set of eigenvalues is 1 and 0. So you can sort of, if you multiply by similar matrices, then this one can shift around, and that wouldn't violate that rule. So intuition can sort of help you a little bit there, but not very far. You need to have intrinsic knowledge of this, which I did not have. So I'll be the first to admit that this problem would have definitely stumped me if it was not for the professor. But honestly, if I have encountered this kind of problem on an exam, I'd probably just give up, because the professor is probably going to destroy absolutely everything in the exam anyways. I mean, this kind of question is absolutely beyond anyone in the class. Maybe 1 or 2 people can solve it. Definitely not me. So, but I mean, it's still fun to think about it and try it out and see what happens. It's not terrible. So enough said. So how do you shift this around? Well, the trick is, when you have this matrix like this, you want to multiply by S on the left and S inverse on the right. So what you are able to do is, let's say you have a bunch of zeros here, this one here. Well, let's just multiply by an example matrix to see what happens. If you multiply by this matrix with everything 0 except a 1 in the second row and the first column, what you end up with is another matrix that looks like this, I think. There's only 1 entry, non-zero entry, and then if you multiply this by something that has everything that's 0 except the second column and the first row, then you end up with everything is 0 except the second column and the second row. That entry is 1. So by multiplying these 2 guys, somehow you have arrived at this. I don't think you even need to be S inverse, actually. You don't need to think about the similar matrices. You just, with this one, you can always multiply by 2 generic matrices in LB so that you can shift the 1 around on the main diagonal. And the trick is you want to shift it so that it goes to the correct row first by using this matrix, and then you shift it to the correct column by using that matrix. Now it's in both the correct row and the correct column. The slight problem that you might encounter with this is that, strictly speaking, you are multiplying by a matrix on the right and a matrix on the left, and you might have some issue justifying that. So just to take a step back, because we are involved in quite a lot of things already, what is already said is that we may force such a matrix like this, like there's a bunch of zeros up here, everything else is zeros. This matrix is in epsilon by performing some reduced row echelon form, and then some multiplication by a matrix that has 1 in the left top corner and zeros everywhere else. You are able to show that this is inside the epsilon subspace, or whatever you may call it. And then you can sort of say that this matrix, you can generate new matrices that look like, so that have 1s dispersed on different spots of the diagonal, zeros everywhere else, which is kind of crazy. Yeah, it doesn't really make too much sense, but you can do this. And then these are all the matrices in epsilon, and then since epsilon is some sort of subspace, it's closed by addition, then if you add all these matrices together, you get the identity matrix. So the identity matrix is also in epsilon, and from here you can proceed the way we did previously. the question is, how do you get from here to here? How do you move the 1 around on the main diagonal? Well, the thing is, you can multiply by some generic matrix here in LV to shift it to the second row first column, and then you can say this matrix is then epsilon, and then you multiply by another matrix that looks like this, and then it's in the second column first row, and then it moves it to the second column, and then so on and so forth. And you do this about n times, and you add all these guys together in epsilon, you get the identity matrix. And the identity matrix, since the identity matrix is an epsilon, any matrix in the linear operator space you multiply by the identity matrix is closed. The epsilon is closed by multiplication against the operator space, so you still end up in the epsilon space. So indeed, that epsilon space has to be the linear operator space, or it contains a zero matrix only. So that's, yeah, I wouldn't yeah, I wouldn't want to do that again, to be honest, because I wonder if the textbook is just more questions like this, because so far I've been able to breeze through some of this, comparatively speaking, fairly quickly. But if I encounter more questions like this, I might not be able to do every single question in the textbook. It might have been too ambitious in the first place, but I mean, I'm here, right? I'm studying this course. That's what I should do. I don't see any other way for me to study this stuff concretely, certainly not in the way that if you receive an A or an A plus or a B, you think that grade has some meaning and you understood something, but not really. You haven't really understood anything. So, okay, anyways, a lot of depressing talk. Let's move on to 3E1. So let's say you have a subspace of the graph. So previously I remember that we proved that if you have a subset, if you have a linear map, then the graph of such a linear map is a subspace. But then you want to show the other way around. If the graph of T is a subspace of V cross W, then T is a linear map. This is what you would like to show as well. So if T is a subspace, of V cross W, then you want to show that T is a linear map. I don't know how you would really approach this, but first things first, you want to lay out all the properties you have, you can get from the subspace. So first things first, 0, 0 is in the subspace. That's fine. And then for any arbitrary elements in the subspace, if you add them, they're still in the subspace. So that's fine too. And also you have some sort of homogeneity requirement. So yeah, so now you got all three. Yeah. So now so how do I show that this is a linear map? So a linear map has, let's see how many requirements it has. So linear map has only two requirements, additivity and homogeneity, or homogeneity. I'm not sure how you would say that. So I think this aligns very well with the subspace requirements, and in fact I think this is the reason why linear maps are chosen to transport subspaces or vector spaces into other vector spaces, because they preserve things very well. And with an injective, with a bijective linear map in particular, you can do isomorphisms because you preserve the additivity and homogeneity, because the linear map is also obeys such rules, I guess. I don't know, maybe I'm just speaking nonsense. So you got this additivity. So let's say that you have some arbitrary 2 points in the subspace T. So let's say V1, W1 and V2, W2 are in the subspace T, right? And let's call T of V1, W1 and T of V2, W2, right? And then v1 plus v2, w1 plus w2 is also in the subspace T, because this T is a subspace. So we know T of v1 plus v2 is also equal to w1 plus w2. So, oh, before I even go there, I should probably define that for every point in the subspace T, of course, that T of the first coordinate is the second coordinate. That's how you would define the linear map first. And then you will proceed this way by showing that the graph of T, since the graph of T is a subspace, then for arbitrary T v1 equals w1, T v2 equals w2, T of v1 plus v2 equals w1 plus w2, because v1 plus v2 comma w1 plus w2 is a coordinate which is in the vector space or the graph of T, which is from the property of a which is from the property of the subspace. And homogeneity follows very similarly. So let's say you have some arbitrary v in v such that T of v is equal to w, but how do you know that then? Yeah, it's not incredibly clear about that. Hold on. Right, so if you have some arbitrary point, let's say VW, which is in the graph of T, then by definition of the linear map based on the graph, then T of V equals to W. Then also multiplying the coordinate results in some point which is still in the graph of T. But this coordinate also is part of the definition for the, let's say, for the, what's it called? For the linear map. So then this property holds because W is equal to T composes V. So I guess linearity and homogeneity holds, but in a very strange, because I don't think I defined that very well to begin with, but here's the thing, like, if I want to do this with good quality, I don't have time, but if I don't spend enough time doing this, it's pointless, so it's very careful balance I have to preserve. So V1 through Vm are vector spaces such that V1 cross everything through Vm is finite dimensional, and prove that Vj is finite dimensional for each j between 1 and m. Okay, sure. So, well, how do you prove something is finite dimensional? You show that there exists a finite basis which spans the vector space, right? And so if V1 cross Vm is finite dimensional, then there must exist a basis which spans this product. So it must span this space. So let's say we call that let's call such a basis, and say it's a set of V11 through V1m. This is one element of the basis, and then you proceed to list out all elements of the basis. Because given that it's a finite dimensional vector space, you find a dimension and you can construct a basis of that dimension. I mean, this is one of the key rules of linear algebra. Well, you may not be able to construct it, maybe, but it definitely exists, right? So we use the existence of such a thing to go here and say that we have this basis, for example. And then I claim that the first element of these guys form a basis for vector space 1, for example. And indeed, if you choose like some arbitrary column in this tuple, the set of tuples, then they form a basis for Vj. A jth column, when formed into a basis, forms a basis for Vj. But how is that? Well, let's say that there exists. So let's say that for V I1 plus okay, so let's say there exists some V in Vi where V is not spanned. V is not spanned by C of V I1 through, or sorry, if you C of 1, okay, 1I, etc. through C of N I, right? So if it's not spanned by this, then what you can show is that, let's say you put the rest of the coordinates as zeros and you put this V in the ice spot. Then this tuple which resides in the product also is not spanned by this basis, because you cannot, just focusing on this one element, you cannot find the linear combination of these guys so that they add up to this V. So it's a contradiction, a proof by contradiction. You can show that indeed no such element exists, and the basis of the product, you can extract the basis of any element of the product, which, since the basis of the product is dimension, and the basis for any element which is being multiplied by in the product is also finite dimensional, because it has the basis is a finite dimensional list. Okay, so give an example of a vector space V and subspaces U1, U2 V such that U1 cross U2 is isomorphic to U1 plus U2, but U1 plus U2 is not a direct sum. Oh boy. Yeah, and U1, okay, and V must be infinite dimensional. Okay, there we go. Yeah, that's terrible. I can already sense this is going to be terrible. Okay. Okay. Yeah. So first things first, when U1 plus U2 is a direct sum, then the dimension of their direct sum is the dimension of U1 plus the dimension of U2, which is the same as the product. Dimension of the product is also the dimension of I don't know how because I know in addition you call them addends or whatever in products. What do they call multiplicants? I don't know, like members or elements that participate in the multiplication. So you do have this formula where if it's a direct sum, then these two correlate directly, and they're the same. But if you do not have a direct sum, then some of the dimensions are missing in the sum, right? So in fact what you have is, like, I think dimension U1 plus dimension of U2 minus dimension of U1 intersection U2. And if this is not 0, then you lose some dimensions which you cannot retrieve from this U1 cross U2. So this U1 cross U2 will always have greater dimension than U1 plus U2 if you are not a direct sum. And this is only talking about the finite dimensional case, and somehow in the infinite dimensional case, the intersection does not lose any dimension on the U1 plus U2, which, I mean, okay, but you can't really think of it this way. The way you want to think about it is because infinite dimensional isomorphisms aren't really about comparing the dimensions of each, unless you're into some weird, like, Aleph no or Aleph 1, whatever you call those weird things. But for, like, this class, I think the only way for you to determine infinite dimensional isomorphism is to construct an invertible linear map. And you want to think in that way because you have some weird, like, sequence shifting that you can do that, like, makes some dimensions disappear while also preserving the bijectivity of the linear map. So you can lose some dimensions easily that way. But this question in particular doesn't seem easy at all. In fact, it seems really annoying. So, yeah, I don't know. I think the trouble is the injectivity, because you want to map U1 cross U2 into U1 plus U2, but if U1 plus U2 have overlap, then the intuition suggests that U1 cross U2 mapping into U1 plus U2 have trouble with injectivity. If you're naive and constructed the linear map poorly, you can easily have some injectivity issues. Oh, jeez. I want to see how many questions there are left in this textbook. So for chapter 3, I suspect there's about, okay, there it is, 37. Okay, so 37 plus 20, I guess. Yeah, if I scroll back up. Yeah, there's about 57 questions left in this chapter, which honestly, if I'm being honest here, I think it might take 2 weeks to complete. If I do this with good quality, but I can't afford that because we are already on chapter 6. Yeah, I haven't been to class in a week or two because I think I've explained already, professor style teaching is quite different from the way I learn, so I don't really gain anything from him. But he's been very helpful about talking about random questions in the textbook. And I've heard people say that he's improving, so maybe I'll go back and see what he's doing. But yeah, I believe he's probably going to finish chapter 6 this week. And he'll move on to chapter 7 probably. But at best, I think like I have a very loose understanding of chapter 5. Even chapter 6 is already a bit beyond me because I haven't read it. I read chapter 5 at least, so it was very shaky reading for sure. So let's see. Let's try to solve this question 3. So I think what I'll do is I'll read ahead. I will read as much as the class requires, but I'll slow down and solve problems from previous chapters, because what I'm thinking is that once I understand enough linear algebra, I'll be able to break through these. There'll be one day when I can break through these questions easily, when in one day I can solve maybe 10, 15 questions. If not, there's still a lot of time before the final week, and I can do so much more before then. Part of me is motivated by the final exam, but part of me just wants to genuinely learn something in this school for once, which a lot of people aren't able to. So this is my last year here, so I'm dropping a class. So at least I can focus on this and understand this, because I'm not that smart. I don't get stuff that a lot of people do. I'm not that fast. I have to slow down and think. So this is just my style. So beginning to think that maybe you can construct some sort of so maybe you can say that U1 is spanned by X. Oh, of course, I want to maybe describe that V is the space of all polynomials over the reals, for example. And then U2 is spanned by the elements X and X cubed and so on. I deliberately avoided from using polynomials of odd or even degree or things like that, because you get left with a lot of lower degree terms that can be kind of annoying. And So I chose to isolate only the highest degree term and put them on here, and this is a more efficient way of thinking about odd degree polynomials, in my opinion, when you're doing things like this. I don't think this will work because u1 plus u2 will generate only odd degree polynomials, while u1 cross u2 will generate what's it called, even degree polynomials, which u1 plus u2 just cannot match those polynomials that have even degree somehow. This is the thing, I saw about all these questions previously, and I realized the answer at some point, but I did so many of these questions, then I forgot them, so it's like as if I never solved these questions. But there's some faint idea of what's going on. I just can't seem to remember. So let's say u1 is spanned by the constant 1, and u2 is spanned by, I think this might have been it. u2 is spanned by 1x to the second x to the fourth, and etc. And then I think this might work. Yes. Yeah. Okay. Right. I think this will work. Yes. Okay. Yeah. This is perfect. Okay. Yeah. I did think about this one. Yeah. So now to construct the isomorphism. Yeah, that's going to be difficult. Okay. So let's say you have some arbitrary 1 3x squared. Where would you like it to map to? The very intuitive choice is 3x squared plus 1, which is definitely in the sum. So, and I think this actually works, and the reason is because, let's say there exists another, and okay, the first element you choose from u1 and the second element you choose from u2, because this is u1 cross u2, not u2 cross u1. But let's say there existed another set of two polynomials from u1, u2, such that this u1 plus u2 is equal to 3x squared plus 1, right? But this 3x squared term you must contribute from u2. And because there only exists oh wait, isn't there also an issue in this? Because you can do 0 from u1 and 3x squared plus 1 from u2. Is that still an isomorphism? Because okay, yeah, no, that's okay, hold on. Okay, that's rough. Okay, so I guess I thought of the incomplete solution. Yeah, I'm not sure how to proceed from here. Actually, I think there's a very small chance I might have taken a picture of something I've written on the blackboard once, but chance is very, very small that I did something like that. Yeah, I don't think I have. Yeah, unfortunately. Yeah, it doesn't look like it. So, well, actually, to show that it's an injective map, all I need to do is show that the kernel is 0, but the kernel is definitely not 0 because there's some elements which you can take from here to cancel out some elements from here, so it's not gonna work. But what if you put also another x here? No, but you can still cancel some things out in the kernel. I was thinking that maybe you could like shift this space somehow. If you do x u1 plus u2, then maybe that. The only problem is this is definitely not in the sum, so that doesn't work, right? This is such a bizarre situation. I don't see a way out of this. Let's say that u2 and u1 are spanned by some arbitrary elements in the polynomial space. As long as they have one element which overlaps, which they must because they're not a direct sum, they must have some non-zero element that overlaps in the basis. And if not, then you can always switch a basis so that they overlap. And then, because what you can do is, there must exist a non-zero element which is in the intersection of u1 and u2, and then you expand that element to a full basis in both u1 and u2. Now you have a basis of u1 and u2 which have a non-zero intersection, or whatever it's called, and then that element you must have some trouble, because then the kernel is not 0, right? You can do 1 times that basis element in u1 minus 1 times the basis element in u2, and then you get 0, which means that for a simple map. And then for something more sophisticated, if you have some, let's say f of x or some, I don't know, q of x, some polynomial times this basis element in u1. Let's say that, okay, so let's say that u1 intersection u2 is v1, and then this is, well, what if you can, oh shoot, okay. Because you're looking for a isomorphism which is a linear map, then you're destined to have some polynomial multiple of u1 plus another polynomial multiple of u2. So let's say this, right? But then like these two guys have this v1 in common. Oh, I actually, if p, q are different, is there a way to avoid this? No, I don't know. This question is beyond me. I get stuck in question 3 of a section. That's not a good sign. Yeah, but I gotta do this soon before all of this escapes from my memory. I don't think I did any question in 3F. Only 3. 3F I did like maybe 5 or 10 because the professor suggested to review those before the prelim, and I went over them with a couple of study partners. But yeah, I think I'm out for the day. I need to spend some more time thinking about this question 3. If it gets me stuck for another day or two, I'll ask the professor. Yeah. Anyways, thanks for tuning in if you still are. In fact, I think I used to think that I would record this for because this textbook has no official solution, so maybe someone might find this helpful, but I think now it's just for myself because a lot of this I don't really even get all the time. So